In March 1944, Wu joined the Manhattan Project's Substitute Alloy Materials, SAM for short, laboratories at Columbia University. Wu was recruited to work on the Manhattan Project's uranium enrichment process. Wu was frustrated, though, by her lack of professorships, but she wanted to aid directly in the Manhattan Project. In fact, eventually, Wu was the only Chinese person who ever worked on the Manhattan Project. In the beginning, though, Wu was originally supposed to just check the radiation effect of the reactor, but soon her responsibilities increased dramatically. The recently issued B reactor, which was the first practical nuclear reactor ever created, was set up at the Hanford site, and it was malfunctioning. It just wasn't working correctly. The problem was it was starting up and shutting down consistently. Wu was able to correctly recognize that the reason this was happening was because of xenon 135. Wu's research also had her study Geiger counters to better detract and enrich uranium. Wu's work on the Manhattan Project eventually led to the creation of the world's first atomic bomb, and that first atomic bomb was later dropped on Wu's home country, China, their biggest enemy, Japan, at the end of World War II in 1945. After the end of World War II, Wu's work at Columbia resumed. She became a full-time professor there in 1958, and in 1975, she achieved true pay equality with men. What an accomplishment. Wu was able to confirm the 1933 theory about beta decay. This theory from Enrico Fermi was that radioactive atoms become more stable and less radioactive as time goes on. In 1956, though, two physicists challenged Wu to prove it in an experiment. These two physicists were Tsung-Dao Lee and Chen-Ning Yang. The two physicists wanted Wu to prove their theory that the conservation of parity was not a part of beta decay. Beta decay is the process of radioactive decay in which electrons are lost. The conservation of parity theory, in simple terms, is that the same identical nuclear particles act in the same exact mirrored way. Wu began conducting her experiment at the National Bureau of Standards in our nation's capital, Washington, D.C. The Wu experiment saw Wu lace cobalt-60, a radioactive version of cobalt, in a strong electromagnetic field at a temperature nearing zero. She wanted the temperature to yield no effect on her experiment, so that's why she determined it would be best for it to be close to zero. If the conservation of parity was still in play during beta decay, Wu assumed then that cobalt-60 should randomly disperse evenly in a bunch of different directions. What Wu actually observed was that the majority of the particles flew off in the direction opposite to the spin of the nucleus, proving the conservation of parity just does not apply to beta decay. Wu successfully executed the experiment, and it was later named after her, the Wu experiment. While it was great that the experiment was named for her, in 1957, the two scientists that challenged her to make the experiment to prove their theory were the ones that received the Nobel Prize for it, not Wu, who actually did and created the experiment, just because she was a woman. I mean, this is sad. Now, I know I mentioned electromagnetic fields earlier, something extensively we've covered in class. Electromagnetic fields, as we know, can have an effect on the behavior of charged particles. Wu, being able to set an electromagnetic field in this experiment, was thus able to control the spin of the electrons that were being emitted in beta decay. Since she now had control of the spin of the electrons, she was able to accurately observe the trends in the path of the emission. There's no variables at play to throw stuff off. The purpose of the experiment was to see if the conservation of parity theory applied to beta decay, and Wu was able to prove that there were directional preferences in the direction opposite to the spin of the nucleus, which disproved the parity and approved the theory that Tsung-Dao Lee and Chen-Ning Yang tasked Wu with confirming.
So now I'm going to be talking about her legacy, but specifically in terms of sexism and how when she was alive she endured through this, but also how after she's empowered many women to the present to keep prevailing through it. So sexism has been a long prevalent issue in the scientific community, and it's been hindering the progress and recognition of women scientists. Chien Wu faced the harsh realities of sexism during her career, but persevered through her immense talent and determination. Her experiences not only shed light on the discriminatory practices she endured, but They also played a crucial role in paving the way for the empowerment of women in science today. And despite her remarkable achievements, she was often subjected to this sexism and faced numerous hurdles throughout her career. And one of the most notable instances that I'm going to be talking about was during the Geddekon experiment, also known as the Wu experiment, and Chase previously mentioned this experiment. And she conducted in collaboration with her colleagues Shiung Li and Chien Yang. And Wu played a pivotal role in designing and carrying out this experiment, which also ultimately disproved the theory and earned Li and Yang the 1957 Nobel Prize in Physics. However, Wu's name was not included in the award, which highlighted the sexism and gender bias prevalent at the time. This exclusion not only reflected the discrimination she faced, but also underscored the need for equal recognition and opportunities for women in science. Wu also mentored women in various academic and professional settings throughout her career. So, as a professor, she taught and mentored students at different universities, including Columbia University and Princeton University, and many of her mentees were women pursuing degrees and careers in physics and related fields. She also mentored and guided female colleagues and researchers with whom she collaborated on scientific projects. Her mentorship extended to informal settings such as conferences, workshops, and research gatherings where she would offer advice, share experiences, and provide support to other women in the scientific community. And right here, the picture shown is her and some of the graduate students who are women at Columbia University. In addition to mentoring and advocacy, Wu actively participated in professional organizations that aimed to support women in science. She became a member of the American Association of University Women and the Committee on the Status of Women in Physics, and they worked to create a more inclusive and equitable environment for women in scientific fields. And throughout her involvement in these organizations, she collaborated with like-minded individuals and contributed to initiatives that aim to dismantle gender barriers and promote gender equality in science. It's still crazy because Wu is getting more and more recognition even till this day. So in 2020, Time Magazine did a project called Woman of the Year where they named 100 influential women in the past that were usually overshadowed. And they did this project because for 72 years they released the Man of the Year, but they never did the woman. And then even after that, in 1999, they changed the title from Man of the Year to Person of the Year. But since then, they still chose a man basically every single time. So finally, they decided to create this project named 100 Women of the Year. So they chose 100 influential women, and one of them was Wu. And I wanted to show the right behind me is the magazine cover of her.